So we don't have any labs on flow sensors. This is one thing you need to understand. What is flow? Well, flow is the rate, right? The rate of usually a fluid moves. Usually we use the term flow for fluids, right? You understand? And what's a fluid? A liquid is a type of fluid. So I'm sitting in a fluid right now. Yeah. Anything that has no fixed shape, it moves freely with pressure, and it takes the shape of whatever it's put in. That's a fluid. So we have two types of fluid. We have liquids and we have gases. For a long time, guys, that's what I thought too. I thought a fluid was a liquid, but no, a fluid can either be a liquid or a what, or a gas. So air is a fluid. Does it take the shape of what it's stored in? Yes. So it has no fixed shape, right? You understand? Does it move freely? Yeah, when wind blows, it moves, right? So, huh? That's a liquid. That's a fluid. It's still a fluid. We call it gas, but it's not a gas. I guess they call it a gas because when it goes into your when it actually goes into your cylinder to fire, it is a gas. So that's what your carburetor does. It mixes it with air and converts it into a gas, and it sprays the gas in there. So I guess that's why it got the name gas. Technically, it's not a gas. It's a liquid, right? Okay, we already know the definition of a sensor, right? And we know this is what we're sensing. So now we're going to sense flow rate. So flow rate is the speed. Flow rate is something moving. Is a fluid in motion, right? Rate is how fast it moves, right? So here's our units. Standard units are liters per minute or cubic meters per second. U.S. customary, or what people call imperial, is gallons per minute or cubic feet per minute. So it's a volume, right? It's got to be a volume. So we're moving a volume. So a gallon has a volume, right? So you'll see it either cubic feet per minute. So cubic feet would be a square of the fluid moving past a what? Moving past a point in a second. So basically, we understand the basic electromechanics of a flow sensor, and a lot of our sensors are like this. I even should use this on light, but light, a lot of it has a transmitter. It's got a sensor, it's got a transducer. What does the transducer do? Yeah, it takes energy in one form and converts it over to another. We can't create energy, we can just change its form, right? You understand that? Uh, and we condition it. We're either going to be analog or digital. So these are examples of flow meters, and all these are looks like they're U.S. customary. Here's one that's not on there. Can y'all see this? GPH. What do you think that would stand for? Hour. Yeah. So that would be something moving pretty slow, right? Are we okay? So none of these show any of the IS standards. I can't see what this is. This is gallons per minute too. So flow sensors are based on differential pressure. We're going to look at an orifice, plate, ventura, and a pitot static. Then what we call a rotometer, spring and piston, turbine, paddle wheel, vane, magnetic flow meters, and ultrasonic flow meters. So this is a spring and piston. This is pretty straightforward. So the flow comes in, pushes against this piston. The piston has got a calibrated spring. I know what a calibrated spring is. I've used that term a lot. Nobody's asked me what that is. Well, it has a certain compression or expansion with an applied force. So it's not just haphazardly made. You know, what determines how much a spring will compress when you put a force against it depends on a lot of stuff, right? The thickness of the metal, how well it's made, and stuff like that. And we've been using calibrated springs for a long time. I don't know. Used to Walmart, they had this is the way we used to do weight and balances. So down at Walmart, I think they still have one over in produce where you can drop it in that little basket in there, and all you're doing is putting your weight against the calibrated spring, and it's going to stretch out so far. And once it stretches out so far, it's going to stop, and that's where the indicator is going to stop on there, right? So we still use these a lot. So what happens is your flow comes up against the front. This is pushing up against a piston that's got a certain area, right? Then we come up there and it pushes that thing, it compresses the spring, and then this guy's got an indicator on the side. So this would be a physical flow pressure. We had these on our old hydraulic trainers that we had. It was the flow meter that we used, and it worked. This is exactly what it used. Okay. So this is the orifice. We use this a lot because one thing, it has really no moving parts. But what we do is we come over here and force the fluid through an orifice. And the size of the orifice, of course, it speeds up right here, right? You understand? And then it comes over here and it creates a pressure differential. So this would be like if I come over here and I measure the voltage drop on this. If I measure the voltage on this guy right here, right? You understand? And I come over here and I measure the voltage right there, then I knew that 2 psi would represent a certain, and I knew the size of the resistor, I could calculate the current flow through it, right? You understand? And this is exactly the same way. Exactly the same way. So what we're doing is we're sending the flow through a precise resistance opposition. We have a pressure drop. We measure that pressure drop, and then the instruments use that to calculate the flow. They're very, very popular. And we do the same way. This impedes it a little bit, right? Gases work pretty good on this, but these guys in liquids, these guys will have a tendency to create what we call eddy currents over here when it comes around. So the other one we use is what we call a Venturi, which basically works on the same principle, but this works on the principle of pressure drops when fluids speed up. And we've seen this before. So this actually creates a low pressure here and a high pressure here. And we actually use this to create vacuums. Anybody that's got a pressure washer, normally they come with a big old tank on it, and then you can run a pipe and plug it into the side and put liquids in there. And when that high pressure or that fast flow goes past there, it goes through a ventura, decreases a vacuum and pulls that stuff right out of that container into your pressure washer. We do the same thing here. So, and we use this principle. Whoever discovered this principle is really neat because this is the way airplanes fly too, right? You understand that? So what we do is we have the air coming up, going over the curve over the top. It moves faster because it's trying to recombine, creates low pressure, high pressure on the bottom, low pressure on the top. And what does it call the plane to do? Lift up, yeah. So it creates a lot of lift. It always amazes me. You get on these big planes, and you know you got 200 or 300 people on that thing, and you look out to them wings, you know, and they might be 8 feet across, and them suckers are creating enough lift to not only lift that airplane and all that baggage they got in the belly and all them people. It's really, really amazing what they can do. So these are Venturas. So both of our lines, both the Festo line and the Amatrove line over in the mechatronics lab uses this principle to create a vacuum. It just shoots pressure through a Ventura, but we're not measuring it, right? You understand? Are we okay? Make sense? These are called P-dot static. I ran into these So what we have to do, we always have to have a reference that we measure our pressure from, right? So you notice both those had a high pressure and a low pressure. It's just like when you make measurements inside your circuit, it's always referenced to two things, right? You understand? You got 2-meter leads. If you only stuck one of them in there, you have no reference, and your meter would be very, very confused. So here what we do is we bring the flow directly into the PDOT tube, and then we come up here, and then we have something that's measuring static pressure. And what it does is it compares both of them, and then this is what it uses to measure flow. This, guys, is most airplanes, this is the main way they measure their speed. Now, what's important why they do this is because what changes when you go up? Well, static pressure changes when you go up. So what they do on the side of the airplanes, they got little holes that are the static, right? And then you got PDOT tubes pointing out front, which takes the flow, and that's what you're doing. That's what these things, we call them PDOT statics. Our PDOT tubes were heated because we could get up to over 32,000 feet what our plane could fly at, which is low for a lot of jetliners, but it's high for a turboprop plane. And so they had to heat the PDOT tubes. And what we would do, and sometimes the pilot would leave them on. So one of the things we used to do when we go, I don't drink anymore, you guys, but we go to the club and they'd have these candles on the table, and we'd put our hand over it and see who could hold it on there long enough to burn all the oxygen, and the candle would go out. So one of our guys, we called him Tex because he was from Texas, of course. He burned his hand real bad, and that's what he told his wife when he went home. He grabbed a hot PDOT static tube and burned his hand on it. So ours were heated, and sometimes the pilot wouldn't. We had to check them all the time, and they had to cover them up, of course, because wasp and stuff likes to go in little holes, right? You understand that? So I had to keep them covered up all the time, and sometimes the flight engineers would flip on the heater and not take off the little covers, and they'd burn them up. But PDOT static, these guys are used very popular. You see how it works. So we take a static measurement, we compare it to a pressure, right, to a force, and then we calculate velocity off of that. This is a very popular method. It's not as invasive as a Ventura, right? So a Ventura and also an orifice, you have quite a bit. You lose pressure inside that. So you might have 100 psi on this side, and you might 80. So you might lose 20 psi just going through the orifice, so you can measure the flow, right? You understand that? This guy here is a lot less invasive as far as. So this is exactly the way they measure airspeed on an airplane. So as you go up, the air gets thinner, the static pressure goes down. They compare that to the ram pressure, and it gives you the airspeed, wherever you're going. Of course, we had different methods. Most airplanes, except for the 737 MAX, right, has multiple backups for what they measure. So the MAX only had one angle of attack sensor, and they didn't have any way of knowing it was bad. So, and what was it doing? I know what the angle of attack is, right? Everybody understand that? So when a plane's coming in for a landing, you ever see them, they're not doing like this, they're doing like this, right? You understand? And what happens is they adjust what they call an angle of attack. So an angle of attack is a relationship to the plane to the direction the plane is flying. So they always do a nose up. If they get the angle of attack too high, then the plane will stall, and then they'll crash. So what happens on those sensors, what was happening, it was telling the plane that it was going to go into a stall, so they dipped the nose down to pick up airspeed. Well, the problem is it was coming in for a landing, right? And they dipped the nose down to compensate for airspeed, and the pilots didn't have time to figure out what was happening. And what happened? Yeah, it crashed through them. Same reason. Angle of attack sensor was bad, saying the plane was fixing to go into a stall. The plane tried to adjust itself, which most planes do that now, right? In fact, most planes will land themselves now. Most of the pilots are just there, and just in case what? Well, if something goes wrong, yeah. So these planes will take themselves off, they'll land. So yeah, you're right. And I mean, they're getting more and more. They're moving more toward that. This guy here is used quite a lot. This is called, my swimming pool had one of these on it until it crapped out on me. But this showed me the flow rate of going of my pump. It showed me the flow rate. Just worked just exactly like this. So what happens is the flow comes in. This guy's got a certain amount of weight that holds it down, right? You understand, flow comes in, causes it to lift up, and how far it goes up would depend on the flow rate. Based on gravity, height of the float indicates the flow rate. Pretty easy, right? This is a vane. This is pretty obvious how this works. This is very, very popular too. So you got a vane. It's got a calibrated spring hooked up to it. Comes up here, flow comes up there, hits the vane. What's it going to happen? Everybody's done this in their car. Sooner or later, you roll the window down, you stick your arm out, get in the flow. What happens? Goes back, right? Okay. This is what a vane does. That's all it's doing, right? And if you knew the strength of your muscles and stuff like that, how far it went back, you could calculate the flow. Well, okay? Yes, no. Yeah, this guy here is pretty straightforward. This is called a vane. Then we have paddle wheel. So this is a paddle wheel. This is pretty straightforward. So we bring flow into one side, move it through there. How fast the paddle wheel turns would give us what? Flow rate, yeah. Most of these are pretty straightforward. Turbine, this is awful. This works very similar to the paddle wheel. Normally, this is nice. What they do is the blades will actually be magnetic, and then we have a Hall effect sensor up there, and every time the thing swings by, it picks it up, and then it calculates the speed depending on how fast the magnets are flying, and it works kind of like a incremental encoder. It's using it to transmit speed. Pretty obvious how this works. I told you about the video. Well, it popped up on one of my YouTube things when I went on there about this guy. I don't know where he is from, but he put these big old magnets out there and he rolled up a coil of wire and he would place the coil of wire in between the two magnets and the fan would run. The little tiny motor would run. And he'd take the coils out and it wouldn't run. Y'all know that's impossible, right? Because to induce a voltage, what didn't he have to induce a voltage? Motion, yeah. You know what they was doing, right? What we figured out, had a hairdryer somewhere, and when he put the thing down there, he'd turn on the air dryer, and they call the little fan, yeah. So that's the most obvious thing that I thought about. And then some of the guys was talking about they had hidden batteries, and if you look real close at the mount, it wasn't the same mount that he showed, but he turned it all around so you could look at it, but you can't see a hairdryer back, you know. So I figured it was a hairdryer. This is a magnetic flow sensor. What's nice about this, there's no evasive. So even paddle wheels oppose, right? Even paddle wheels, you'll lose flow, right? You understand that. Moving vanes, you'll lose you'll lose a little bit of flow because they have what? They all have opposition. This guy here has absolutely no opposition. So what we do, this has got to be some type of conductive liquid. That's the only drawback. And then what we do is we expose it to a magnet. Then we move it through two sensors, and the rate of the flow would induce a voltage back into the sensors that would be proportional to the speed. So the advantage of this guy is it has no opposition to the flow itself, right? You understand that? But the liquid has got to be some type of conductive, so distilled water would not work on this. So this will probably be some type of slurry or something like that would, which is a real thick. Are we okay? Yeah. Fluids must be conductive or non-distilled water based, which most of our liquids are. The Doppler effect or time of flight. So what's a Doppler? A Doppler is a shift, right? And this is basically the way, the best way for them to see a tornado. They look for a shift, air moving in one direction and air moving in another. So Doppler radars pick up the shift, right? You understand that? So what we can do is we can have flow. Depends on sonic conductivity. So the particles or the flow has to be able to carry sound, right? You understand, or pass through it. Affected by temperature, density, and viscosity, unsuitable for high accuracy. So what we do is we shoot a beam down. The beam goes into the fluid. The fluid is in motion. It causes the sound to shift a little bit. And what these guys do is they measure that phase shift. Right? You understand that? It's like a train. You ever hear a train coming at you? And it starts getting real loud. And then all of a sudden it gets really, then it changes pitch on you because it's going so fast. It's pretty neat. So basically you're kind of sensing a Doppler effect when they shoot the whistle out and when it goes past you and then it comes back. So, everybody okay? So these are ultrasonics. The problem is any sound would be viscosity. And what's viscosity? The thickness of a fluid, right? Here we're usually talking about liquids, right? But so that's what when you buy oil, that's the viscosity, you know, that they're giving you on the side. The weight is actually the viscosity. So what we do is we have a real lightweight that handles, that lubricates your engine in the cold weather, and then we have a heavyweight that basically lubricates and they shift around, right, when for hot weather. So we have at least two viscosities on our oil now. So used to run one weight all the time, and then your engines didn't last near as long as they do now. So engines now they last a long time, guys. Yeah, when I was a kid, if you got 100,000 miles out of a car, you got a special tag. You could buy an antique car tag, and you could drive with it. Now you can only get an antique tag if you don't do what? If you basically don't drive it, because so many cars started going over 100,000 miles, and these antique car tags was, good gracious, like a third of a regular tag that you would buy. And people started using it. They'd be driving around. You see antique car tags all over the place. So they did away with that one. So the other one is time of flight. This basically works the same way. We shoot it through at an angle. The time it takes to go through the liquid and then be reflected by it would be a measurement of how fast it's flowing. This is probably very, very accurate about 1% of the flow rate, which is pretty good, ain't it? Handles bidirectional flow. This is unaffected by temperature, but these guys have got to be mounted at an angle, so you can see them. They're pretty obvious when it's there. I think we got some pictures on the next slide. We okay? Somebody say, I heard Bernard, he's trying to write it down. Is that the only reason we're waiting? Just to write it down. So here they are. So these would be the ones that are permanently mounted inside the fluid. And notice this guy here is pretty wide, so they got transmitters and receivers across it. Here's one that would be put onto the pipe external. This right here, I don't know. This looks like it might be Doppler. I'm not really. This looks like this used to be Doppler. And that, oh yeah, they are Doppler. And that one up there is Doppler. So Doppler, both the sensors are going to be mounted on the same side. In time of flight, they're going to be mounted on opposite sides, right? Everybody okay there? Yeah. Now they're still trying to draw these. Of course, you can always look at the PowerPoint slide on Blackboard. So that's basically the flow sensors. Is that all of them? Probably not, but that's all of them that I could come up with. Why? Because I figured that y'all would retain this for motor controls, but undoubtedly you haven't. So what we're going to do is make sure we go back over the rules for relay logic. because I've seen some interesting things when you started designing your own. Now, of course, when you design it and you draw your diagrams up, you have to use industry standard symbols. You cannot make up your own symbols. So what you have to do is you have to, and I need to print those off and let you look at them also. Industry standard symbols, right? You understand that? Control devices such as switches, push buttons, relays, and relay and sensor. This should be, y'all need to make this correction, guys. These are relay contacts. Y'all making that correction, please? So control devices such as switches, push button, relay contacts, and sensor contacts must be placed between L1 and the rung's load, because the relay is a load, right? Understand that. Output devices such as relay coils, lights, motors, and solenoids must be placed between the control devices and L2. One and only one output can be placed in each rung line. A rung is an electrical circuit that runs between L1 and L2 that consists of at least one line. You got to have at least one line, right? And we could have more. Magnetic motor starter overload contacts are the only thing that's allowed between the motor starter coil and L2. All other rung loads must connect directly to L2. So how many loads in a line? Control devices can be connected in series, parallel, or series parallel. The connection of the control devices does not determine if the circuit is a series parallel or series parallel circuit. We do not have series parallel circuits in motor controls. You understand that? We have parallel circuits, or we have single element series circuits, single load series circuits. Multiple rung output devices cannot be connected in series. However, multiple output devices can be connected in parallel in a different line within a rung. Only one output device can be connected in a rung's line. The rule is one or more output on a rung, but only one output per line. There is no series parallel circuits allowed in relay logic diagram. And there's no multiple load series circuit either, right? Control devices such as switches, relay, and sensors with a single contact can only be used once in a relay logic diagram. Control devices that have multiple contacts can be represented multiple times in a relay logic circuit, but the same contact cannot be used can only be used once. Y'all understand that? Who broke his rule? Yeah, you did. Joe Barry and them used the same contact, what, 5 times? I think it was 5 times. 3. Of course, that's why we use watt in this class. That's why we use manufacturer numbers, right? I require you to use manufacturer numbers. Each relay rung output or load must be assigned a name. The name should be written above each rung load. The name is usually an abbreviated version of the function of the relay within the control circuit, or the load, yeah. Each contact controlled by a relay must be given the same name as the relay that controls the contact. Everybody okay there? Output devices can only be represented once in a diagram. So we can't have the same output multiple times like you can in a PLC. Don't get PLCs and these guys confused with each other. One of them is a program, one of them is hardwired, right? You understand? All control devices and output device symbols must be placed horizontally. Signals in a relay logic diagram must flow from L1 toward L2. Signal flow must never flow back toward L1. Diagrams should be numbered and commented correctly. Unlike PLC diagrams, horizontal lines and numbers are on relays. We number rungs. On motor controls or relay logic, we number lines, right? You understand that? So a rung can have multiple lines. It's got to have at least one line, right? All lines, the location of each relay contact controlled by a coil is identified by writing the line number on the contact's location to the right of L2 and adjacent to the coil symbol that controls the contact. Multiple contact line numbers are separated by what? Commas. A normally close contact location is underlined. These numbers are referred to as numerical cross-reference numbers. All lines must be drawn either horizontally or vertically. We have no curved lines. That's also true in electronics. All conductor connection joints must be identified with a filled-in circle or a dot covering the connection of the joint. Everybody understand that? Okay. This is a rule that we break a lot, especially in PLCs, because PLCs don't follow this rule. I don't even think it does it on the Siemens. I'd have to look at that too. So the rules that I've seen broken is multiple loads on a single line. And then, of course, trying to use the same contact multiple times. So this is like NCIS where Jethro has his rules. You ever watch NCIS? Bernard knows some of the rules. I've learned them over time too. And guess what I do? Huh? So everybody made that correction, right? Okay. This is the plane I used to work on, by the way, SP3s, when I was in the Navy. Big planes. Biggest plane that the Navy flew. Okay. What else do I want to show you? So I'm going to have to remember next class to go back